Okay, how are we? It's our last video lesson for this unit, and what I'm going to do today is I'm going to give you one more equation for us to use. It's my favorite. We call it the ideal gas law because gases that essentially have no intermolecular forces and ones that aren't under a lot of pressure and aren't really cold, they will always behave according to this. And really, it's every equation we've already talked about kind of put together into one. So here it is. Here's the equation. PV equals nRT. PivNert. I would put this on my car's license plate, except it looks a little bit like pervert, and so I don't want that on my license plate, but how sweet would that be? You'd know oh, there's Log driving down the street with her PivNert license plate. P stands for pressure, V is volume, T is temperature, N, we kind of saw this in the last video. I don't know why, again, they picked this, but N is for moles. We can do stoichiometry with this, so get excited. And then we've got one new variable. We've got the letter R in here. Again, don't know why they picked the letter. R has a name. It's called the ideal gas law constant. It's a constant. And here's what I'm going to do. I'm going to give you R. R can be 0.0821. The units that R has are liters, ATM over mole Kelvin. So remember how density is grams per milliliter? This is the units for R, liters, ATM over mole Kelvin. R can also be 8.314, there's a point there, liters, kPa over mole Kelvin. And R can also be 62.4 liters mmHg over mole Kelvin. So these are the constants, and it's like, Log, you said R is a constant, totally said it was a constant, and then I gave you 3 different numbers that R can be. I want you to notice when you look at the units, how the units are essentially the same, except for in each of these, the unit of pressure is different. So you would pick your R value, the one that you would use in the equation, depending on which unit of pressure you're using in the problem. You ready to try one? Okay, let's do this. Here we go. Okay. Whoa, here's a problem. What pressure, notice how I've specified in mmHg, is exerted by this many moles of gas in 4.08 liters at 35 degrees Celsius? We've got all the variables. Let's use PivNert, the ideal gas law, except we're going to solve for P. So to get P by itself, I'm going to divide both sides by P. Whoops, I divided by the wrong one. We're going to divide both sides by the volume to get P alone. Let me get rid of that guy. And all we need to do is plug the variables in. So I'm going to take 0.325 moles. R, like I said, can be one of these 3, but in our problem, we are using mmHg, so I'm going to pick the R value that has mmHg in the unit. So I'm going to use 62.4. So I'm going to do 0.325 moles times 62.4. I'm going to write the units, liters mmHg over mole Kelvin, times the temperature. Do you see how it says 35 degrees Celsius? What unit does that have to be in? You're right, it's Kelvin. So I need to add 273 to it. So that gives me that the temperature is 308 Kelvin. All divided by the volume, which is 4.08 liters. Check this action out. Liters go away, moles go away, Kelvin goes away, and I'm left with the one unit we were solving for, mmHg. And I get, I believe, 2.01. I did the problem wrong on my sheet of paper I'm looking at. I solved for it in ATM. But now that I'm seeing this, hold on, I'm calculating. Oh, it's just like we're in class. Log screwed it up even in her practice run. Calculating divided by 4.08. I get 1,530. What problem did I do? 1,530 mmHg. Ta-da-da! Okay, we did it. Problem 1. Want to do another one? You do? Perfect. So do I. we're going to use the ideal gas law again. PV equals nRT, except now in this problem we're solving for temperature, so if we do PV divided by N and R, we get temp. So in this problem, pressure is 725, we're just plugging variables in. The volume is 8.77 liters, divided by the moles, which is the letter N, 1.45, and then we've got that problem of figuring out the R value we're going to use. It's mmHg. The R value that has mmHg in the unit is 62.4, so I'm going to write my units over mole Kelvin. Multiply the top, multiply the bottom, and then when you divide, I get the answer as being 70.3, but what unit is it? Good question. Liters go away, mmHg goes away, moles go away. What's the only unit that's left? It's Kelvin. And you can keep your answer in Kelvin if you wanted. But if you wanted it in Celsius, you would just subtract 273. Cool. That's great. There's fun stuff we can do. We can figure out like the molar mass of a gas. We can figure out the density of a gas. Density, if you remember, is mass over volume. Usually for gases, since they take up so much space, we use the units of grams per liter. And molar mass is the mass that a mole weighs, so we would write grams per mole down here. So let's try one. This problem is asking for the molar mass. So my answer needs to have the units as being grams per mole. So if we read through, do you see how I already have grams? Boom, half the problem is done. Now the only other piece they need to find to get the units up here that I'm looking for is I need to figure out how many moles of the gas that I have. To do that, I'm going to use the temp, I'm going to use the pressure, I'm going to use the volume, and literally we're just solving for moles using the ideal gas law. Since I don't know what gas it is, I can't just look at the periodic table for it. So for this, we are going to rearrange Pivnert to get moles by itself. So we've got PV over RT equals N. And so I'm just plugging stuff in. So 0.874 ATM. It's the pressure times the 1 liter all over. Notice how the pressure is in ATM. We're going to pick the R value that has ATM in the unit, and that number is 0.0821, and I'm going to write the unit ATM over mole Kelvin times the temperature, which is 28 degrees Celsius, but we have to turn it to Kelvin, so I'm going to add 273 to it. So I got, I think, 301, and when I did this, I got 0.0354 moles. I'm not done though, because we want our final answer to have the units as being grams per mole. Now that I know the moles, I'm going to take the gram value and divide it by that, and I get a molar mass of 31.9 grams per mole. That's really cool, log. I know, it totally is. Let's do another one. This just keeps getting more fun. Oh, density. We need the units being grams per liter. And we're talking about ammonia. To make this easy, let's assume you have 1 mole of ammonia. Great. So how would I figure out the liters that 1 mole of ammonia takes out? Remember when we said that 1 mole equals 22.4 liters? That's only at standard temperature and pressure, which is 0 degrees Celsius and 1 ATM. Notice how we are not at 0 degrees Celsius and we are not at 1 ATM. So you can't use that 22.4. That only works at STP. So for this problem, because we've got this new tool, Pivnert, we just need to figure out the volume. We've got everything else. So I'm going to simply just divide by the pressure, plug everything in. Like I said, we're going to assume we've got 1 mole. It's at ATM, so I'm going to use ATM's constant, 0.0821 mole Kelvin, and our temperature, which is 63 degrees Celsius. plus 273 to get it into Kelvin, I got 336 Kelvin, all divided by our pressure, which is 0.928 atm. So I got that this gas takes up 29.7 liters. And I want the units for my answer to be grams per liter. So remember how we said this is ammonia? And I said we're going to assume we have 1 mole. Add together the nitrogen on the periodic table and the 3 hydrogens, and I get that its mass is 17.04 grams. I'm going to write grams for 1 mole. So I can take that, the gram, 17.04 grams, and divide it by the liters of 29.7 liters, and I get that the density of this gas is 0.574, and I'm going to write grams per liter, and that's my final answer. Which makes sense. Gases are way less dense than water. Water has a density of 1. So if you ever end up with a gas density that is above 1, something happened. You know what's even more fun? We can do stoichiometry. Everything's the same, except now, notice, it's not at STP, so we can't use that 22.4 number that we used last unit. But we can use PIV, NERT to kind of solve what we're looking for. Problems are the exact same. We take the number we're starting with, which I'm going to write out, 725 grams of, I thought it would be fun to throw tungsten in here because it's W and we like never see it. So it's like, whoa, 725 grams of whoa over 1. We're turning it to moles because that's always our first step. And I use the periodic table in my dining room, so my sig figs may be a little bit off than the pink periodic table I gave you, but I got that its molar mass was 231.8 grams for every 1 mole. Not done, because we're solving for hydrogen gas, so we got to get there. So I'm going to write moles of whoa on the bottom, and I'm going to put moles of hydrogen up top, and the ratio is 1 to 3. So for every 1 whoa, we're going to need 3 moles of H2. And I'm going to leave it there because I can't really take that number any further. And what I got is we would need 9.38, I'm going to write moles of H2, and H2 is a gas. That means we can use the ideal gas law. What's the problem asking for? Liters. So I now know N, I know the temp up here, and I know the pressure up here. All we're going to do is solve for the volume using the ideal gas law, plugging in all of our variables that we know. So N, the number of moles, is 9.38. I'm going to write moles of H2 times the R value. Since pressure is in mmHg, I'm going to use 62.4 liters mmHg over mole Kelvin. And the temperature is 20 degrees Celsius, so plus 273 to it. I got 293 Kelvin, all divided by the pressure, which is given in the problem, is 730 mmHg. So it's a little bit more work than using that 22.4. But in the end, I ended up solving that with this 9.38 moles, I would need 235 liters of hydrogen gas to use up 725 grams of tungsten oxide. It's fascinating. It's the only way to get good at this. Practice. Go for it.